We've been spending our time in heredity up to this point dealing with how things are supposed to work, whether that be with a trait that's complete dominance or incomplete dominance or codominance or whatever the trait might be. How should it work? But things don't always work the way they should work, the way they are intended. When things don't go as planned, it's called a mutation. A mutation is nothing more than a genetic mistake, and we're probably all filled with them. We're going to deal with a few of those today, with the understanding that you don't know quite enough about DNA at this point to really have a true understanding. So we will come back to the idea of mutations in more detail at another time, but it's important at this point to at least get a sense of what they are. Pictured here, you can see three different types of pretty common mutations. The first is a deletion, and then translocation, and then an inversion. It's important to note for all of these that in order for your traits to actually be expressed, in essence, your genes, your chromosomes need to be read. Your body needs to read them and put them into action. And so I want you to think of these chromosomes kind of like you're reading a book. And let's just say that the book happens to have 10 chapters. So in our first example here of deletion, this is a very simple concept. Here's the chromosome in its entirety. And you can see a portion of it here in the middle with an X through it. Just imagine that portion of the chromosome being cut out, and then the top portion and the bottom portion, which were not cut out, then joined together. And that's what you're seeing pictured over here. The problem, of course, is what's in the X. That portion of the chromosome is just, as the name implies, deleted. It's lost, it's gone, it's never to be heard from again. And so if you imagine that whole chromosome as a 10-chapter book, just imagine removing, let's say, chapters 4, 5, and 6 from that book. Yeah, the other chapters are still there, but they also don't make as much sense as they used to. A second type of mutation is a translocation. Now, in order to understand this, we have to have two chromosomes pictured. You can see here they happen to have chosen chromosome number 4 and chromosome number 20. In chromosome 4 and 20, in this case, a piece of chromosome 4 is cut off. A piece of chromosome 20 also cut off. Now, unlike what we just talked about, those pieces, despite being cut off, are not deleted. They're not lost. Instead, they just swap places. And so a big chunk of chromosome number 4 is going to join number 20, and a little chunk of number 20 is going to join number 4, and you can see the resulting combinations of chromosomes over here. Now we need to think of these things as two books. You can imagine it would be pretty strange to take chapters 9 and 10 from a book and chapters 9 and 10 from a different book and have them swap places. You haven't lost anything. All of the material, all the content is still there, but now both books are rather confusing. And that's really what would happen with both chromosomes 4 and 20 in this idea of translocation. Lastly, we have a mutation referred to as an inversion. This one is perhaps the strangest of the three. We're going to start off with our chromosome here on the left, and like deletion, a portion of this chromosome is going to be cut out. Unlike deletion, again, where that chunk of a chromosome is lost, instead, it flips itself upside down and then reinserts itself at the very same place that it used to be. Again, nothing is lost. It's all still there. But again, imagine the idea of a book where you take out chapters 4, 5, and 6, flip around their order, and reinsert them in the book so that you read chapter 1, chapter 2, chapter 3, but then you go immediately into 6, then 5, then 4, and then pick back up with 7, 8, 9, and 10. It's all still there, but it's not going to have the same meaning, and the result is a mutation. Now, those are all pretty generic, and as I said, you'll have a greater understanding of exactly why they cause problems in our next unit. The one we want to spend a little bit more time on here is a mutation known as non-disjunction. Now, in order to understand that, let's talk about how things should work. And this is something that you're already familiar with. Pictured here is a cell, and you can see one homologous pair of chromosomes. You know that there are 23 pairs of homologous chromosomes in a human cell, but we're only picturing one of those pairs right now. And what should happen is that one member of that pair during meiosis 1 should end up over here, and the other member of that pair should end up over here. And then during meiosis 2, each of those dyad chromosomes should get ripped in two so that you end up with one here, one here, one here, and one here. Since we're talking about mutations, obviously things aren't going to go the way I just explained, because that's the way that they're supposed to happen. Initially, when this pair split, one there, that's known as disjunction. And so if that doesn't happen properly, it is non-disjunction, as is labeled. And so you can see what can happen. Instead of one here, we end up with both members of this pair going to one cell during meiosis 1. Now, it is important to note here, although you can't see it, the other 22 pairs of chromosomes all did what they were supposed to have done. I realize this looks like a blank cell over here. It's not. 22 pairs of chromosomes split up and did properly what they were supposed to do. Half here, half there. What's being pictured is simply that one pair of chromosomes that screwed this up. Ultimately then, where you should have had one here, one here, one here, and one here, we end up with 0, 0, 2, and 2 for whatever this particular chromosome pair happens to be. Let's just say, for instance, that it happens to be chromosome pair number 18. You have 0 of number 18 here, 0 of number 18 here. You have 2 here and 2 here, where you should have had 1, 1, 1, and 1. There is another way for non-disjunction to occur. It happens instead in meiosis 2, so that you can see in this particular case over here on the right, everything happened normally in meiosis 1. One member of the pair here, one member of the pair here, everything's good. And whereas this one proceeds normally and ends up with 1 and 1, the non-disjunction occurs in meiosis 2 instead, and you end up with 2 here and 0 here. Any way you look at it, we've got problems. Now, what's the result? Because, of course, what we've made down here at the very bottom, these all represent gametes. These should all be haploid sex cells that are the result of meiosis 1 and meiosis 2. What if this sex cell fertilized this normal one? So here we have an abnormal, here we have a normal. The result, and again, let's just assume that this chromosome that we have pictured up here is chromosome number 18. We have 0 of number 18 coming from this parent. We have 1, like it's supposed to be, coming from this parent, and therefore the baby, the zygote, is going to only have 1 of chromosome number 18 instead of the pair that it's supposed to have. That's one possible wrongdoing. Another possibility, let's say this sex cell of one parent fertilizes a normal sex cell, as is the case over here. Now, this parent is contributing 2 copies of chromosome number 18, and this parent is providing the normal number of 1. The baby, the zygote that would result in that union of gametes, would result in 3 of chromosome number 18 in that baby instead of the normal number of 2. So you can see the prefixes down on the bottom, mono and tri. Where a baby ends up with 1 copy of a chromosome instead of 2, we call that monosomy. And where a baby ends up with 3 copies of a chromosome instead of 2, we call that trisomy. As I've gone through this diagram, I've said that the chromosome pair that screwed up in non-disjunction in this case was chromosome number 18, but understand that it could have happened to any of them. There is monosomy 2. There's trisomy 2. There's monosomy 17. There's trisomy 17. There's monosomy 8. There's trisomy 8. So pick any of your 23 pairs of chromosomes and enact the idea of non-disjunction, and you're going to end up with either a monosomy or a trisomy condition for all of them. For example, if we look at the karyotype here, which is simply a picture of somebody's chromosomes, you can see that what they're supposed to be is a pair of chromosomes in each case, 23 pairs of chromosomes. But for the X chromosome down here, there's one. There should either be a second X chromosome, if this is a female, or a Y chromosome for a male, but there's not. In other words, this person has monosomy X. And you can see that labeled at the bottom. You can see it says karyotype, and then it says 45, X. In other words, there are 45 total chromosomes instead of the normal number of 46. And the one that screwed up is that there is only one X chromosome. There is monosomy X. Another example, if you look here, you should be able to pick out the problem. You can see that there should be 23 pairs of chromosomes. Instead, there's 22 pairs. And if you look at number 21, you've got 3 of them. In other words, this person suffers from what would be called trisomy 21. Also the result of non-disjunction, but trisomy instead of monosomy. And it happens to be chromosome pair number 21 that screwed up instead of the sex chromosomes. Yet another example. You might not pick it out at first, but there is a problem here. The problem is over here. You should have a pair of chromosomes here, either an X and an X or an X and a Y, but definitely not both. This person has XXY. In other words, they have trisomy XXY, and you can see that at the very bottom. It lists 47, XXY. There are 47 total chromosomes, and the extra is one of those sex chromosomes. So instead of XX or XY, there is XXY.